Hey, what's up everybody? We're going to do two quick examples here. I always like to go back and revisit the idea of Lewis structures for good practice, and it's also a good way to help identify which gas molecules will deviate more significantly from ideal behavior. Remember, the more polar the molecule is, the more likely it is to deviate from ideal gas behavior. So a quick review here, if you've forgotten how to draw Lewis structures, we're going to start with coming up with the Lewis valence dot diagram for the atoms in our compound. In this case, it's just oxygen, and there are 6 valence electrons, which you should recall you can easily identify based on the group number that that element is located in. We've got 2 atoms of oxygen in our molecule of oxygen here, which means I've got 12 valence electrons to work with. We're going to divide that number by 2 to get electron pairs, and we have 6 pairs of electrons to work with in our molecule of diatomic oxygen. We don't really have a central atom to work with here since they're 2 identical atoms, but I'm going to put them side by side and connect them with initially a single bond. I've used one of my pairs. I have 5 pairs left. I put those pairs around the terminal atoms to satisfy the octet rule. I use 3 pairs on this oxygen. I use 2 pairs on this oxygen. Okay, so I've used all my pairs, but now I need to think about my structure. Does this structure correctly represent the Lewis structure for a molecule of oxygen? Answer, no. Oxygen must follow the octet rule. However, I used up all my pairs, and I don't have any pairs left to give it. Remember, in an instance like this, we'll simply take electrons from an atom that it is bonded with and create an additional shared pair. When we do that, we complete each oxygen's octet. Now, for the purpose of this video, once we've drawn our Lewis structures, we want to think about what the molecular geometry is. This will be a linear molecule. Additionally, both atoms involved are the same atom, and therefore the electronegativities are the same. Neither one of them does a better job than the other in attracting the pairs of electrons in that bond. Therefore, this is also a non-polar molecule. And so ultimately, based on polarity alone, we would indicate that this gas would not deviate significantly from ideal behavior, due to the fact that it's a non-polar molecule. Yes, there are London dispersion forces that act between molecules of oxygen, like all molecules, so there will be some deviation, but based strictly on polarity, we would say no.